Any question from previous class? It's pretty straightforward. Okay. I think homework also should be straightforward.
Are you stressing on this one?
Just one question. Find the boundaries.
Oh. It's like all the other previous steps lead up to that.
E not E or EE? Indirect.
It's E not, it's free space.
Okay.
But for linear dielectrics, then it's what's the polarization? And the polarization is the susceptibility.
Yes. You exert the answer.
And this is your dielectric constant,
Yes.
your relative permittivity, unitless.
Yeah.
That's your total permittivity. Well, your full permittivity. Free space times your dielectric constant. It's just the constant that just is like, oh well, it's this and that's harder for this material to become produce an electric field. So this is for like the second and third part. For the first part, you have to consider a Gaussian pillbox. So you take some little pillbox, you squeeze it down, very small. So we have all these pillboxes over this plane. So this top part has an area A. We don't consider it the height because we're taking it as infinitesimally small. So there's height on top, height on the bottom. A plus A equals 2A. So if we add up all these little pillboxes, we have Gauss' law. Charge enclosed, which is So this is just 2A. We have So we have some charges on top.
So then plate for lightning etc. for that.
So for this problem, we have positive charge, and on the bottom we have minus charge. So you make some axis. Top is positive Z, bottom is negative Z. Then we have some charge on the top, sigma over 2. So then we can find our direction. Normal to the surface. So that's how we start part A.
Yeah, I might need this board today.
Oh, sorry.
Yeah. Let's get started. So last time we introduced the different crystal systems, right? If you remember, in 3 dimensions. So we had, if you remember, we had like 7 systems, right? Bravais lattices. But some classes, systems have more than 1 crystal type. In altogether we had 14 different crystal lattices. So that's what I was saying. If you give me any new crystal system, so I can fit into any one of these 14, right? So then I think if you think of this one, we are going to talk about something called point groups and also the space groups. So 3-dimensional, usually we have 32 point groups and 230 space groups. Space groups, I'll talk about these things in details. But if you consider one-dimensional lattice, how many crystal systems you have? Only one, right? You have just simply these crystals, right? But you can think about some crystals having between 2 points, we have something called this, like in 2 dimensions, this is one kind of crystal system, but even if we have one in the middle, that is a different lattice but in the same crystal system. So like that, one dimension you have only one kind of lattices, but you can have 2 different systems because you can have in the center, right? So point groups actually have only 2. 2 dimension, because this is important. Now there are so many 2-dimensional materials, right? Starting from graphene. I think if you look at, there are 5 lattice systems. Lattices, but they belong to only 4 systems, because this system is not, if you consider this one and this one, they are the same lattice, but there are 2 different lattices. For example, if you take, these are the 4 different lattices. This is definitely one square lattice. So then they have a hexagonal lattice. Then you have this oblique. This is more like a rhombohedral in 3 dimensions, right? But you can have this rectangular one, this one, and this one. But here, so the same thing, except there's one central. We don't consider these as 2 different lattice systems, but these are 5 different lattices, but they belong to only 4 systems. 1, 2, 3, they both belong to one system, please remember. If you look at these point groups and space group, you can see the number of groups you have. So yeah, these are the ones we talk about, right? So n square, rectangle, so these 2 belong to one crystal system, right? But they are different lattices. So this is why we need to talk about everything. This classification comes from not just the arrangement of lattice point, it's by the symmetry. Symmetry is the most useful thing, how we do this lattice classification. So I don't know how many people have taken formal group theory class. Any of you have taken group theory? No, that can be, like, I took one when I was a graduate student. It's called the group representation. It's a whole semester is about group theory. It's pretty intense course. I will give you maybe 10 minutes introduction about this group theory. What's really a group means? You have elements in the group, then you need to have identity element, then you need to have 2 operators. When you operate, your third resulting element should be also in the group. Then they have some associate rules and things like that, right? So it's a basically group theory. So, but if you think about the symmetry, so there are so many different symmetries. Symmetry means you have some operation. After that operation, your system will look exactly the same, right? Just think about this one. You have water molecule, oxygen and hydrogen. If I take this one and rotate by 180 degrees, so only thing happens is this become this one, right? Since hydrogen molecules are identical, this looks the same. This is a symmetry operator, right? So this is actually rotational kind of thing. Later we are going to talk about after rotation, if I take a mirror image from a plane, so that is called a roto inversion. So we'll talk about the thing later. So then what happens if I take a mirror here, then this one comes bottom and these 2 will be here, right? So these are symmetry operations. So when you talk about this symmetry, like I said, so that's what I was talking about. In a group, you need to have the symmetry operators, then you get the other element, then you need to have this identity operator and things like that. So these groups we are talking about, you can group into two groups. One is the point groups. Point group means you do mostly rotations, sliding, all these things, but whatever the rotation, one point in the crystal should stay same. That's why we call it's a point group. Space group is mostly translations. Translation plus maybe rotation, translation plus reflection. So those things mostly account for the space group. Like if you take 3 dimension, you have actually 32 these operators. You have 270 this space group operations. So we are not going to talk about all of this, right? But there's one thing everybody should remember. There's something called the 5-fold axis symmetry. So you can, if I take something like this, right? Oh, yeah. So if I rotate this one, you have to rotate by 180, right? To make the rotation. If it is a rectangle, 90 degree, not the rectangle, if it's a square, by 90 degrees, you make that one, right? So that depends on the angle. But there is no such thing as something called 5-fold axis symmetry. If you rotate by this, we call it 360 divided by 5. So if you rotate by this angle, you never get a symmetry operator. That's why we take this pentagon here. If you rotate, you will never get a same structure. So there's no such thing as 5-fold symmetry. You have 1-fold is always there, right? That means you don't rotate or rotate by 360. If you rotate anything by 360, you get back to same thing, right? So that's we call this a 1-fold. So if you rotate by 180, we call this a 2-fold. Typically we call this 360 divided by that number, this fold. If n equals 2, that is 180. That means that's a 2-fold symmetry. If n is 3 means 120, right? If you rotate by 120, you get the same structure, we call it a 3-fold. Like 90 degrees means 4, right? N equals 4. That's a 4-fold symmetry. But there is no such thing as 5-fold. Please remember, n is not equal to, this is never exists. So if somebody says there's 5-fold symmetry, he's saying something not correct, right? Here. So here, this is what I was talking about. The symmetry typically we define by the Cn notation. N equals 2, n equals 3, n equals 4. You can see no n equals 5, right? So then there's another notation called the sigma. Sigma means reflection. If I take a mirror plane, right? If you take a reflection, if you see the same structure, it has a sigma notation. Then I is the inversion. Inversion means completely everything is, so if you take like this, so you have inversion center, then this point becomes this point, right? This point becomes this point, this point becomes this point. R becomes completely minus R. That's called the inversion. So the typical inversion is, first if you take this one, rotate by 180, then take the mirror image. If I take this is my mirror, then what do you see? Bottom. See this one, right? What did you do? First you rotate by 180, that is 2-fold symmetry, right? Then you take the mirror image from this one, then I will show you how that one. Please remember, inversion means first rotate by 180, then you take the reflection, typically about the plane perpendicular to that rotation axis, right? I'm rotating about this one. Then you take the mirror perpendicular to that. So that's what inversion means. Here are some of the things you can, the translation everybody. So if I go from this point to that point, if it's a crystal, it's a symmetry operation, right? Everything looks the same. But this is the mirror reflection. Like, this is my mirror. If I do this one looks like this one, this point, this one, right? But here, if I take xy, x prime is negative x, right? But how about y? Y doesn't change, right? It's the same. So this is the inversion. So if I rotate by, if you take this one, I rotate like this, then I took the image, right? If you do this one, every point becomes minus. If you have r, this becomes minus r. If you do that one, you have something called the inversion center. Here, this is the inversion center for this structure. You can say this point coincides with this one, this point coincides with this one. This is the inversion, that's center of symmetry. Is that clear for everybody? So then there's something called the gliding. Gliding means both, we are going to glide and screw. Gliding means first you translate, then take the reflection. So then the screw means you translate, then you take the mirror. Sorry, the rotation. Yeah. So here you can see this one. I first translate, then I take the reflection about this one, then you see this one, right? So that's the operation of glide. But here they don't look the same, right? That means it's not a symmetry. But if you have symmetry, when you do this operation, this should look like this one, right? The screw means same thing. You first translate, then take the rotation. That means you from here you just rotate by say 180 degrees, then you get this one, right? Still this one and this one different. That means this is not symmetry operate, but this is the operation we are doing. So whether you get the thing, that depends on the object. So I think anybody, if you are doing material science or something, you will see this notations. There are two special notations. There's something called the international notation, that basically 1, 2, 3, 4 like that. Then there's something called the Sean Flies notation. So these are used in different ways. So typically inversion, that means any object, even if you take a triclinic structure, it has a inversion symmetry, right? Because same object, you can make it to same thing by inversion. That means that is one. So this is typically happening in what crystal? Triclinic structure, right? So these are, we already talked about C2, C3, C4, right? These are Cn. So in international notation, they are marked as 2, 3, 4, 5 like that. So no 5, right? So 6. So don't worry about this one. So this roto inversion means you like rotation, then take the
Professor, always rotating clockwise direction?
No, it doesn't matter which way you are going here. For symmetry, it doesn't matter this way or that way, right? Yeah. So also, if you have a two-fold symmetry, that means what? 180 degree, right? Typically, if you see anywhere this kind of notation, this one or sometimes like this means two-fold symmetry. If you see somewhere triangular, this way or this one, this means this is three-fold symmetry. If you say somewhere like this or this one, this means four-fold symmetry. There's no five-fold symmetry, right? If you see somewhere like this or this one, this is more like six-fold symmetry. Anywhere you see something like that. So only think about this one. Here it's getting a little complicated. Don't worry about that. These are still the rotation, right? So how you rotate it. So for example, if you look at this one, take a cube. If you take cube, you have definitely mirror planes. Mirror planes means if you take this one this is a mirror plane, right? Because if we cut from here, this side and this one look like same, right? How about this one? That's also mirror plane, but this is not, because this is not a, if there's a square, that will also be a mirror axis, right? Mirror axis means from that axis both sides should look the same. But if you have a cube here, you can see what is this one? That's a fourfold symmetry, right? That means you have this axis from all 6 directions, right? So that is a fourfold. So 6 means actually it's the same thing, right? You have this one, you have this one, and you have this one, right? If you rotate by 90 degrees, no, not this one, I'm talking about cube. So then you have 3 fourfold, exactly. That's why I have this one, this one, this one, and so, but this and other side, that's the same, right? So this and this one, same, this one and this one, same. That's why you have 3 fourfold axes. Then if you look at 4 threefold axes, threefold means 120 degree. Just think about these body diagonals. If you take the body diagonal, if you rotate by 120, you get, that's why we have this triangular one here, from here to the other end of the diagonal, right? From here to this one. You get the idea, right? If you have a body diagonal, so you rotate by 120, you get same. So that's why we have 4 of those. Then you have 9 mirror planes. That's clear, right? You have this one, all 9 planes. You have 9. So then 6 twofold axis. Twofold axis means rotate by 180, right? So that you have 6 directions, right? You have to think about that when you get the idea. So please remember, what is this notation? Twofold symmetry, right? That means 180 degrees. This means threefold symmetry. That means 120. This means fourfold. That means 90 degrees, right? So these are the things. Here, if I have a orthorhombic means ABC all are different. Then you have less symmetries, right? You have 3 twofold axes. Twofold means it's 90 degree one, right? So then 3 mirror planes, and you get the idea. So here I have drawn all these to make it clear, right? These are all the, these are all twofold, fourfold, right? 90 degree rotations. So here they have all these threefold ones, 4 of them. These are the twofold axis, 9 of them. Right, just go through this one, these symmetry operations. This is not important, yeah. So then, I don't know how many you have. Some of you are working on material science, right?
I do.
Yeah. So you see some crystal structure. A lot of time people write that one, sometimes they have no idea what they talk about. Like if you say like, I have F3M3 bar kind of space group, what does that mean? Most of the time people, nowadays there are software, right? So if you give these parameters, they give you the space group. But always good to identify what that means. So always it comes with one letter. The letter, remember we talk about P for this primitive, then you have I, then you have F for the face center, then you have A, B, C, if they are not in all 6, then sometimes you have this rhombohedral. These are the letters usually come here. Then they have this, you have threefold axis, then you have mirror plane, and things like that. So that's what I want to give a little to, at least to have some idea. For if I take something like this one, so in this one, you can draw actually 3 twofold axis, right? Twofold axis means rotate by 180 degrees. So if you look at this one, this one, this two. If you rotate by 180 degrees, They're symmetric, right? That means you have 3 two-fold axes. They are marked as A2. So also this makes sense, right? What does that mean? It's two-fold symmetry, right? So then, can you see 3 mirror planes? So one is this one, other one is this one, other one is this one, right? You can see here, one mirror plane, other mirror plane, then this one, right? You have 3 mirror planes. So another important thing is the two-fold axis are normal to some of the mirror planes, right? Can you see this A2 that is perpendicular to this mirror plane? Because this mirror plane and this one perpendicular. This one and this mirror plane are normal to each other, right? So if you have this one, usually we write this as this one, 2m, 2/m, 2/m. What does that mean? 2/m means two-fold symmetric axis that is perpendicular to mirror plane. You can see it, right? If you take this one that is perpendicular to that mirror plane. That's why this slash comes here. Is that clear? This is axis that is perpendicular to this mirror plane. That's why this slash means. You have 2 or 3 of them, right? 2/m, 2/m, like that. If you see something like that, please remember, this means these two-fold axes are perpendicular to the mirror plane. If it is not perpendicular, you just write as 2m. That means you have mirror planes, but that two-fold axis is not perpendicular to the mirror plane. So look at this one. So this axis is not perpendicular to any of the mirror planes, right? A2, in this one I have only one two-fold symmetry axis. Is it perpendicular to any of these mirror planes? A2 is only perpendicular if you had a mirror plane like that. But there's no such thing, right? That means how do you write this one? Basically two-fold symmetry, you have 2 mirror planes, right? So we have one two-fold symmetry axis, right? That's only this one, because this is a less symmetric object here. Then I have how many mirror planes? 2, but none of them is perpendicular. This is wrong, right? You only write. Please remember those notations. So you can look at this one also, how that one should look like. So here you will see actually this 4-fold symmetry axis. This is actually, that means 90 degrees, right? So they can be, this is perpendicular to this one. That's why you have this 4. Then you have 2-fold symmetry to this one. You get the idea, right? If you put any slash, that means that fold symmetric axis is perpendicular to the mirror plane. So there are some of the things you can compare. If I take triclinic crystal, you only have one inversion, right? So monoclinic, you have one two-fold symmetric axis with one mirror plane. If you go to cubic, you can have 2-fold, 4-fold, and 3-fold, right? So they all can be there. So these are the notations. These are some information. I think what I want you to learn is, if you see some kind of crystal notation, so you should have some idea what they talk about, right? So first letter tells you what kind of crystal structure, primitive or something like that. Then everything depends on your fold symmetric axis and the mirror planes, whether they are perpendicular to this one. Okay, I don't want to go through too much details. So we already talked about these things. So you can see here, even two-dimensional one. You can see if you take the square, you have 4-fold symmetric axis, then you have mirror planes and things like that. Please go through this one and see whether you can make sense of all these things. Okay, so that slightly different concept, but it's pretty straightforward idea. We have time. So this whole thing, let me write down this one here. Maybe I'll turn on this. Right. So let's think about some one-dimensional lattice. So if this is a lattice, so at any point, right? So suppose if you have atoms can have charge or dipoles or some other properties like spins and things like that. But if you consider any property, lattice, they have translation symmetry, right? So that means any property, suppose Fr at a given point, so suppose this one has a location at say Fr. This F can be anything. It can be some property, just name anything, charge or dipole distribution or spin distribution or any property. This is the property at that point R. Now if I go to another point, suppose I have a translational vector T, right? Suppose T can be written as if this is a lattice constant A, T has to be what? Some integer number of A, right? If you're three-dimensional, remember this T was some m times A1, n times A2, 4 times A3, like that. But here I have only A, right? So that means I can write this one as some n times A, right? So T is basically n times A. So that means if at this point, if this property is Fr, if I go to some point Fr plus T, T is the translational vector, so that can be something like this. If this is a real lattice, what do you think about these two? Should be the same, right? That's the translational symmetry. If this property at this point and this point should be the same thing. Is that clear? So now I can write, if you have any property that depends on this periodic dependence, right? I can write this one as some kind of Fourier transform. Everybody can make the Fourier transform, so that means I can write this one as some coefficient times exponential. So that should have the periodicity of 2 pi over A, right? So this has A times. So now we are writing for any R. So then I am going to sum over all the n times A. This is, if you have any periodic function, I can write this one in this form, right? So any thing I can write as this, because this has this periodic variation. Is it clear for everybody? So that means ideally I can write this one as F as some kind of vector, say some AG. If I write this one as, actually I should be, sorry, because this is all, I write cosine and sine. Everyone remember this? Ix means cosine x plus I sin x, right? Everybody remember this one. That means you can write cosine x as EIX plus E minus IX over 2, or sin x as EIX minus E minus IX over 2i, right? We know all these relationships. So that means I can write, actually you can show here. So this is the one I was trying to say. In the Fourier transform you can write as this kind. You can see 2 pi over A, then you have to have R, and also you are summing over all the n's. But also we know if R plus that T can be some integer times A, right? So T means any, this one, so that also should be here. Or ideally you can write this one as some, if I write this one as 2 pi, so this one, let me write this one, N A N E I 2 pi N over A times R. I'll write this one as G. I'll say why that is. So if I write this one as IGR, so that means I am summing over all the AG vectors here. So I can say G. So this is the same thing. I just replace this part 2 pi n over A by G. So 2 pi over A times n is I write as G. Exactly. So now if I do like this, so now if I write these two functions, so fr I can write as G A G E I G R equals fr plus t. What is fr plus t? Wherever r you have to replace by r plus t here, right? So that means this becomes not in this one. Yeah, right, in this one, right? Fr, is this clear? I'm going to use this equation. Fr, I write as this one, AG, EIGR equals fr plus t is what? R is replaced by r plus t, then I get G, A, G, E, I, G, R means r plus t, right? Because this is r plus t, I can write as IGR times EI, G, T. Because if you do this one, you get r plus t, right? So, okay, now if you take this one, you can see this one doesn't have any independence, right? So that means I can make these two cancel. That means in order to have these two equal, what should EIG2 should be? 1, right? If these two has to be equal, this IEG2 has to be 1. So that's what we are going to show. This EIGT should be 1. That's the requirement we need. So you can see how this is done here. You are to have this invariance. Invariance of what? That f function, right? Should have EIG to be 1. That's the basic requirement. So this means, let me try to, actually you can follow here, right? Is this clear for everybody? If it's a periodic function, you can write as a function of Fourier series. Then I replace this function as G in one-dimensional case at least. So if you want to calculate from here AG, how do I calculate AG? You have to take the inverse Fourier transform, right? If I want to find AG is basically, you just multiply FR by E minus IGR. E minus IGR, then you have to integrate over R. So then you have to do in a cell, so that cell has a unit of 1 over A. So that is, don't worry about that.
That's a Fourier.
Inverse Fourier transformation, right? So if I know this one, you just multiply by minus of this one and integrate it right over the cell. Well, that's not important. So important thing is, if I have this periodic invariance of your property, I can always find this translational vector G, right? Sorry, translational vector T, so that E I G dot T should be 1. That's the basic idea. So the T can be in this case we just wrote T as some constant times A. But in 3-dimensional, what is that value? T is the the primitive vector, that is m times a1, n times a2, or O times a3, that is the function. So that's the whole idea. So, but important thing is, please remember this relationship. If you have a periodic relationship, but what is this G? In the two-dimensional case, we define as 2 pi over A times N. In the one-dimensional case. So, is that clear for everybody? So what I am going to say is, in 3D lattice, you can have your this G vector we define with T equals given by, actually, so sometimes I write these different numbers. So if I write T as, so in this case I write as U1, U2, U3, doesn't matter, right? U1, U2, U3. These are all, what are U1, U2, U3? Integers, right? Cannot be fractions. These are integers. That means belong to that C, right? So actually, with this, we define from this G something called the reciprocal lattice. So I'll explain what is the meaning of that G. So this is what I want to, this kind of very abstract idea. So how we go from it's real space, because real space, this is, please remember this one. So real space, you have this, say A1, A2, A3, then we have these lattice points, right? So any lattice point you can write as, in this case, so U1 of A1, U2 times A2, U3 times A3, right? So now this will define you all the real space lattice points. Now we are introducing this G vector, so that this E I G dot T equals 1, but T is given by also this is by translating by this vector you get to the next point, right? So that means I can define a new space that has unit of inverse T, right? If T has a unit of what? Real length, then the G should have inverse one. So for that one we introduce this new space called reciprocal vectors. So here these are real space translational vectors, or the primitive vectors. Now we define G vector as some different vectors B1, B2 and B3, right? So they all have inverse of real space. So we define as V1 plus V2 plus V3. So this will define some kind of space in the something called reciprocal space. So just like we had A1, A2, A3, now we have B1, so B1, B2 and B3. So again you have the same, these are all integers, belong to this C. So you can easily find, because this, if you take that G and your T, they should be related by this relationship. So that can be satisfied by introducing this B1, B2, B3 this way, like B1 is given as this 2 pi, this relationship here, 2 pi over your volume of your real space times this A2 cross A3. And B2 is given by, because this one has volume A cube, right? So that means if you divide, this one has two length scale, this one has 3, that means you have 1 over 8, right? So you can see how that. Then B2 becomes 2 pi over V times A3, no sorry, this is B1 should be A3, A1, B1 should be A3, A1, and so on. Here I have all the relationships here. B1 is given by B1 should be A2, A3, yeah. B1 should be A2, A3. It's a cyclic, right? B1 should be A3, A2, sorry, A2, A3. So then B3 should be again 2 pi over V. B3 should be A1 cross A2. You can see the cyclic relationship right here. Please look at this one. 2 pi over V, B1 is A2, A3. These are real space one. B2 becomes A3 minus A1. So B3 becomes A1 over A2. That V means real space unit vector space. That means V means really A1 cross A2 dot A3, that triple dot product, right? So if it's a simple cubic, A1, A2, A3, A, right? So that becomes A cube. So if this clear, so this is what we are, here is the V, A1, A2. So this is what I want to emphasize you. So we have real space vector. From that we have A1, A2, A3. Now we are going to introduce new vector so that this relationship is, this is the key. So from that we define something called the reciprocal space that has very similar to this Aik dot R relationship, right? If this is R, this is K, that's the wave function, right? That's K is 2 pi over lambda. So that kind of relationship here. So what, you have 1 minute, but I want to just give direct relationship between these two. This real space and reciprocal space, they are reciprocal space kind of abstract and not real space, but what you are measuring has some relevance. So if you take an optical microscope, you are just looking through your lenses, you are seeing the real image, right? But if you go to like a transmission electron microscope or something, what you are seeing is a diffraction pattern. So this diffraction pattern is something happening in the reciprocal space. So this has a real. So let me give another example. So just think about the real space. These are real space lattice, right? So now if you take this, suppose my unit vectors are A1, A2. So this is A1, this is A2, right? So now if I draw the plane, so what is this plane? So this is x-axis actually in that case. That means this is intersecting at 1. So y is not intersecting, right? That means that is infinity. That means you have 1, 0, right? So that is the plane, right? So this plane is 1, 0, 0 plane. So now this vector n100 is perpendicular to this plane. So this is real space picture, right? So now if I go to the reciprocal space, all these planes, you have millions of these planes, right? All these planes I can replace with one point in the reciprocal space. So you have an origin here. So all these planes I can replace by one point. So that is given by this 1 over d 100. So now if I draw another plane, I think this will make you. So now if I draw this plane, what is this plane? So x-axis is now infinity, y-axis is cut by 1, that means 0, 1, 0. So that's the perpendicular 1, 0, 0. I can draw one point here, 0, 1, 0. That will represent all these planes. In real space we have millions of these planes, right? But I can represent all these planes by this one point in the reciprocal space. So that separation is actually 1 over, remember it's inverse, right? So like that, if you go to this plane, if you take this half plane, that means this is 0, 2, 0, right? Because remember this is cutting at infinity and half and infinity, that means you get 2, 0, 0, right? So 0, 0, yeah, because x and y different way. Yeah. So now all these planes I can represent by point here, 0, 2, 0. Like that, any planes in the real space you can replace by this new space given by these points. This is the G space we were talking about, right? The reciprocal space. So that each point, what is this point? This represent all the planes in the real space. So in that particular direction. So this is actually 1, 1, 0, right? This is 2, 2, 0, like that. So all the planes in the real space you just represent by one point in the reciprocal space. That's the whole idea. So now you can imagine now when you want to calculate properties in a real space. So it's pretty difficult, right? So how if you can do that one in the reciprocal space? That's much simplified, right? So that's the whole idea of why we want to do things in the reciprocal space. I will start from here next class. Yeah. Okay. Then we'll calculate the reciprocal space properties. And okay, I'll stop here. Just little abstract how you go to the reciprocal, but you should understand why we do that. Maybe you should go get the ice.
Oh.
Yeah. We have class here, no?
Yeah.
Oh, yeah.
Yeah.
I had brought
Only
my
do we calculate the
because I thought you would leave it.
Oh, you leave it here?
Then when students submit, we can.
I put this one out because I thought you would touch this again.
Oh, okay, yeah.
Okay, thank you.
That's good. Rishi?